Welcome back to Physics 3740 at the University of Utah. Today we're going to take a first look at the phenomenon of wave-particle duality, which is a very central idea in quantum mechanics. So as we sort of build towards developing a more formal development of quantum mechanics, this is one of the next steps. Okay, so we've seen that we have the situation where photons, we have good evidence that light behaves as a particle that we call photons in these experiments which we've done. We've discussed Compton scattering, we've discussed the photoelectric effect and Planck's law, but we also know that we think about light as a wave as well. So this lecture is going to be sort of exploring this sort of two faces of quantum particles, and I guess really the question that we're trying to answer in this lecture is, what is a photon? And so what is this quanta of light that we've been discussing? And if we ask that of pretty much anything, I think the answer actually gets more complicated than we might at first imagine. For example, if we asked, what is a tree? The answer that you would get would likely depend on who you asked. For example, if you asked, some people may base, a perfectly reasonable answer would just be to sort of describe the physical attributes. For example, you might describe an average size of a tree or of a kind of tree, something about its mass or weight, color, but if you ask a botanist, for example, they may say something quite different. They may say how it originates, how a tree originates, how it grows or develops. A biochemist might talk about its chemical composition, the cellulose that makes up a tree, the chlorophyll that makes up that's in the leaves, and so on. And so each different everybody that you ask might give you a slightly different answer, and so it turns out that a tree is actually a rather complex thing, even though we kind of know what a tree is. The description of it is rather complex. And the same is true of basically a photon. Okay, so you would have to answer this question from a variety of perspectives. So for example, you could describe its properties. You could say that it has, for example, we know that we've discussed that photons have no rest mass, okay? And because of this and the energy momentum invariant, you get this relationship here, that the energy of a photon is equal to its momentum times the speed of light. And Planck's constant tells us that the energy of a photon, the Planck's law also, or Planck's hypothesis, is that the energy of a photon is also related to its frequency here, okay? So E equals h nu. Okay, this is Planck's hypothesis, and this is the energy momentum invariant. Okay, and then we also know that photons move at the speed of light, and so if you from Planck's hypothesis, then you can get this relationship with the speed of the wave is speed of light, c, constant, and you get that the energy is also equal to Planck's constant times speed of light divided by the wavelength. And so those are some basic properties. We also know that, at least under some conditions, that the photon interacts as a particle. So we've done we've talked about the Compton scattering, we've talked about the photoelectric effect, for example, as I mentioned, that reveal a particle-like behavior. And but we also know, although we haven't shown it directly, but we will be talking about it today, that light also travels as a wave, and we can see that because we know you should have seen in some previous classes that you get a diffraction patterns and interference effects when you have light waves going through slits or and so forth. So we have the properties actually of light of a photon are these are some of the properties that we've already discussed.